Now, one of the questions you might want to ask yourself is, well, how can we detect the frequency, or in other words, how do we detect the pitch? So the frequency, of course, remember that sine waves can vibrate at very low frequencies where there's just a few waves per second, or at very high frequencies where there's lots of waves per second. So how do we detect that? Well, there's two ways that our basilar membrane detects frequency. One is which fibers are responding. So there's specific hair cells that, depending on the frequency, fire. So we think that certain hair cells on one end of the basilar membrane might vibrate more for low frequencies, and certain hair cells at the other end of the basilar membrane might vibrate more for higher frequencies. And it's also how the fibers are firing. Not only which ones are firing along the basilar membrane, but also if they're firing very slowly or very rapidly. So we use those two pieces of information, the location of the fiber on the membrane, on the basilar membrane, as well as how fast it's firing, to be able to detect pitch. So one of the earliest theories of how the basilar membrane works was put together by Becke's place theory of hearing. And basically, it's a fairly simple theory. What he said was that the frequency of sound is indicated by the place on the organ of Corti that has the firing rate. So once again, imagine the organ of Corti, right? And then you have the basilar membrane running down the middle, and on top of the basilar membrane you have the organ of Corti, right? And what his idea was that a frequency would cause the vibration of a certain spot on the basilar membrane. So if this is the basilar membrane, maybe low frequencies would vibrate here on the basilar membrane, right here. And then here's the basilar membrane again, and then maybe high frequencies would cause vibrations over here. So low and high. So all of these would mix together to produce all of the sounds that we hear, but low frequencies would be in this spot and high frequencies would be this spot. And the way he figured this out was he actually took cochleas out of cadavers, dead people, and he was able to observe in actual human cochleas the way the basilar membrane behaves in response to vibration. It turns out he was able to detect that the basilar membrane does have certain spots where it'll vibrate for low frequencies and certain spots where it vibrates for higher and higher frequencies. The other thing that you can do is you can actually build a model of the cochlea using the physical properties of the basilar membrane, and it will in fact vibrate in this way. If you were to build a huge replica of the cochlea with this basilar membrane in the middle of it and then send frequencies through one end, it will in fact vibrate specifically in certain spots based on the frequency that you're putting through it. The part of the basilar membrane that's by the stapes is very narrow, and then as the basilar membrane goes, it gets wider and wider and wider. So it's physically different at near the stapes than it is away from the stapes. It's thin at the stapes, and then it gets wider at the end. It's also stiffer at the end, so it's kind of soft by the stapes, and then as it gets closer and closer to the apex, to the end, it actually gets stiffer. So we believe these properties of the membrane allow it to vibrate preferentially at different spots for different frequencies. And we've been able to observe also that the motion of a sound wave travels across the basilar membrane as a traveling wave. So it travels as a traveling wave, and it vibrates preferentially at certain spots based on the frequency. Now, the traveling wave has what's called an envelope. A wave, of course, is made up of these little ups and downs, right? But the envelope is like the entire shape of, if you were to take all those little ups and downs and put them and wrap them or draw lines around them, that would be the envelope. And it turns out that there is an envelope of a traveling wave through the basilar membrane. So the envelope at one point is going to be bigger, where in a certain spot for higher frequencies than in another spot for lower frequencies. Wherever the envelope is the biggest for that traveling wave is where the hair cells are going to be most activated, and we believe that point that is most activated will give us the indication of what frequency we're listening to. So this is a picture of the basilar membrane. It's a little three-dimensional picture of the basilar membrane. Remember that the basilar membrane actually is thinner at the beginning, at the base, and then it gets wider as it gets to the apex, and also it's stiffer at the apex than it is at the base. So it's real soft and pliable here, but it gets stiffer as you go higher and higher. This picture shows a traveling wave of 3 frequencies going through the apex. And of course, if you were to wrap each of these 3 frequencies, you can actually create an envelope that kind of starts here, and then it goes to the blue line, then the green line, then the red line, and then the blue line, the red line, the green line, and the blue line. That's the envelope, and that's what we see here is this traveling envelope wave. And wherever you see the highest amount of stimulation is where the hair cells are going to be vibrated the most. And we believe this is one way in which we're able to detect pitch, is where on the basilar membrane that wave is causing the most vibration. So here's a very simple linear example of an envelope for different frequencies. So this line represents the basilar membrane, and this is the base of the membrane, and this is the apex. Base, apex, base, apex, base, apex. So if you play a 25 hertz tone, which is a very high-pitched sound, very high-pitched. I'm sorry, 25 hertz, that's very low-pitched. Sorry about that. If you play a 25 hertz tone, which is a very low-pitched sound, it's going to create this envelope here with maximum vibration here. A 100 hertz tone, which is a little bit higher in pitch, will create this envelope, which has the maximum vibration here. 400 hertz, maximum vibration here, and then finally 1600 hertz, maximum vibration here. So notice each one of these pure tones creates a different pattern of vibration on the basilar membrane. There is on the cochlea an orderly map of frequencies along its length. So we know by measuring the responses of the cochlea that the apex, which is the wide stiff part at the end of the basilar membrane, responds best to low frequencies, and the base, which is the thinner flexible part, responds best to high frequencies. This is called a tonotopic map. We have actually mapped out the cochlea, and we know that it's laid out to respond best to, going from the base highest frequencies all the way to the apex lowest frequencies. As a matter of fact, here's a picture of a tonotopic map. Here's the base of the cochlea right here. So this is where the stapes is. And this spot right here is best for 7,000 hertz. This spot right here is best for 5,000, all the way down to the very end, to the apex, where we've got 200 hertz, 150 hertz, 125 hertz, 75 hertz. So you notice as we go from the base of the cochlea all the way down to the apex, down the length of the basilar membrane, that the frequencies get lower and lower and lower. We also have neural frequency tuning curves that we've used. We'll send a pure tone through to be picked up by the cochlea, and we can actually detect which pure tones a particular neuron is most sensitive to. And we've actually plotted these. We've measured individual output from neurons inside the organ of Corti, and we have found that neurons at particular spots in the organ of Corti are more sensitive to particular frequencies. And each neuron has what's called its characteristic frequency, the frequency that it responds best to. So here's some of the data, right? This is going from the apex all the way to the base, and these are recordings of neurons. Notice that we have lines that start high and go low. The lower the line, the more sensitive a particular neuron is. So we've detected two types of neurons: the neurons that are indicated in green and the neurons that are indicated with the dash lines, and have measured the output, the firing rate of each neuron as a function of the frequency and the decibel level. So we have neurons here that respond to low frequencies and neurons that respond to very high frequencies. And they only respond within certain thresholds between, say, 80 and 20 decibels. So it's beautiful evidence for this place theory that we have these neurons that are preferentially sensitive to specific frequencies at specific amplitudes or loudness. So what if you're deaf, right? What are some of the causes of deafness? Well, one of the causes of deafness may be the fact that your cochlea or your inner ear is damaged. And now we have these things called cochlear implants, and you've probably seen them in the news or whatever. There's some videos in YouTube where there's deaf people that are getting cochlear implants for the first time in their lives, like little babies. There's one with a little baby that's hearing its mother's voice for the first time, and it's real cute. And there's another one with some lady who's getting a cochlear implant for the first time, and she's crying because she can hear. And they're really neat. But basically what they do is they have a little array of electrodes that they actually put directly onto the cochlea to stimulate the nerve fibers. So this is presuming that the cochlea is okay, but there's been damage to the rest of the ear. So, or maybe the cochlea itself is damaged, but the organ of Corti is okay. So what they'll do is they'll do microsurgery to stick a little array of electrodes, and it's like a little tiny little wire, and they'll just stick it in there, and that little wire will run along the length of the organ of Corti. So it'll sit on top of the organ of Corti and be able to stimulate different spots on the organ of Corti. And then this little electrode assembly is attached to a microphone that gets worn behind the ear, a sound processor, that analog to digital sound processor that takes the analog sounds and converts them into digital. Then the transmitter is mounted on the bone, and then a receiver is mounted in the bone and attached to the electrodes. And people are then able to actually hear. So here's the little wire inserted into the cochlea, and here's the receiver, and here's the transmitter. These are attached directly to the bone under the skin, and then on the outside you have the transmitter, which sits behind the ear, and then on the inside you have the receiver. And this is a close up of the electrode as it goes into the cochlea. So it goes into the scala tympani, and it winds its way around. And this electrode is actually has lots of little points here that can be stimulated, and based on the pattern of sounds that the external receiver hears.